So in today's video, we're looking at representations of the special linear Lie algebra of arbitrary dimension. And once again, as always, we're working over a algebraically closed field with characteristic 0, and everything is finite dimensional unless otherwise stated. All algebras and modules. So, first section is notations. Let n is going to be an integer, at least 2, and we're going to let g be the special linear Lie algebra of that dimension. Which, if, as a quick reminder, is the elements of the set of matrices of n by n over Rk, where we write them as components like this. And they're the elements of the n by n matrices with a trace of 0. Since the center of G is 0, and that our base ring, our base field K, and to the nth power is an irreducible G module. We have that G is semi-simple. And you can also get this by looking at the Killing form. G is, it says here, G is actually simple, but we won't be using it, and it's harder to prove, so we just won't really care about that here. And now we are going to define we're going to let H be the Lie algebra of diagonal matrices, of diagonal matrices H with elements lambda 1 through lambda n along the diagonal, with, of course, this is the special linear, so the sum of these diagonal components must be 0. We're then going to define n positive to be the Lie algebra of strictly superdiagonal matrices. That is, matrices of the form where xij is 0 for I greater than or equal to j, and we symmetrically have n negative being the Lie algebra of strictly infradiagonal matrices, which you can probably intuit what the definition is going to be. xij is equal to 0 for I less than or equal to j. So essentially h covers everything along the on the diagonal, and positive everything on one side of it, and negative of everything on the other side. And because n positive and n negative have to be 0 along the diagonal, they automatically have trace 0, and so there's no additional constraints on those. This gives a decomposition as I mentioned. We can think of G, any element. We can look at the elements of one side of the diagonal plus the elements on the diagonal plus the elements on the other side of the diagonal. Note that H is abelian since it essentially corresponds to the algebra on k to the n with component-wise multiplication. And that n positive and n negative are both nilpotent, as essentially every time you multiply, the number of zeros is going to move over by one index, so eventually it's going to subsume the whole matrix. And for n equals 2, we have, this looks like the positive, H is the matrices of the form x, 0, 0 minus x. We've seen this before. And positive is the component. It's only one component above the diagonal in this case. And of course, and negative is our elements below the diagonal, which in this case is once again just parameterized by one variable. And we're also going to put b to be equal to h plus n positive, so it's all the elements on or above the diagonal. So then b is a solvable subalgebra of G with its derived algebra giving us n positive. We're now going to let H star, as you can imagine, be the dual of H. So an element chi of H star can be written. This is why up above we explicitly wrote out elements of H as a list of lambdas. So then chi of an element H is equal to the sum of ui times lambda I for some ui in k and h being decomposed into lambda 1 through lambda n as we saw above. And as we saw, we know that h has the constraint that the sum of these lambda i's has to be 0, so the trace is 0. The ui constants which determine chi are only determined up to the addition of a constant. Now, we're going to let R positive be the subset of H star of linear forms lambda I minus lambda j for I minus j. So I believe this is like the element of chi where ui is 1 and uj is -1 and I comes before j. And we're going to let R be the union of R positive and the negative of R positive. Keep in mind R positive is not like a subalgebra or anything, so there's no, we don't have that kind of structure on it. So an element alpha of R is called R, or respectively R positive, is called if it's R positive, it's a positive root, but it is in general a root. The positive roots of alpha I is equal to lambda I minus lambda I plus 1. So it's the difference between successive roots are called the fundamental roots. So that we see that any positive root can pretty obviously be written as a sum of fundamental roots. Any positive root alpha equals to lambda I minus lambda j. We see above I is less than j. Be written as alpha is the sum from n equals 1, n equals I, to j minus 1. So we're essentially just telescoping the sum here. Now we're going to let alpha equals lambda I minus lambda j be a root, not necessarily positive. Then define elements h alpha and x alpha of g as, we're going to define x alpha. I'm going to write it in better notation I think than they have is going to be Eij. So the ijth entry of this matrix is 1 and everything else is just 0. And we have H alpha as being the element of H with lambda I equals 1, the jth coordinate is -1, and everything else, I guess I should be better, I think, to write it as e to the ii minus e to the jj. So the component at e at I times I, the ith component of the diagonal is 1, the jth component of the diagonal is -1, everything else is 0. We want to note that alpha of H alpha is equal, we see here, of, it's going to be 2 as being E_i times lambda I plus -E double j. So the E_i is going to contribute 1 times the lambda I, and the E double j is going to contribute -1 times the minus lambda j, so we get 2 essentially. Now we get a proposition. This comes in 3 parts with no preamble. The set of all x alpha for alpha in R positive, make a basis of n positive with the basis of x negative alpha for alpha in R positive, making likewise a basis of the below diagonal elements B for all matrices H along the diagonal and elements alpha and RR, so I guess it's a root. I'm trying to keep track of notation. Then the bracket of H and the matrix defined by alpha is equal to the root alpha acting on H times our original x alpha. So it corresponds to scaling. And C is at the bracket of x alpha with its negative is H alpha. Now the proof. A is clear because any element of n positive is just a number with I greater than j, corresponding to lambda I minus lambda j as root alpha, so that's automatic. And for B, let H have diagonal terms lambda I from 1 to n. If alpha is the linear form of lambda I minus lambda j, then H dot x alpha is equal to lambda I dot x alpha times x alpha and x alpha times h is equal to lambda j times x alpha. Hence, the bracket of h and x alpha is hx alpha minus x alpha h. We can factor out these lambda terms to get lambda I minus lambda j x alpha, which is just alpha of h times x alpha. And we get similar for C. So I'm going to look at an example of how all this works here. For the two-dimensional case, the only positive root, there's only two different lambdas to choose from, so you only get one positive ordering, which consists of alpha being lambda 1 minus lambda 2. The basis of SL2, we've seen it a couple times already now. Just as a refresher, is H alpha is 1, 0, 0, negative 1. X alpha is of course going to be 0, 1, 0, 0. And x of negative alpha is going to be 0, 0, 1, 0. Perfect. Alright. Goes on to our next chapter here, which is weights and primitive elements. We're going to let V be a G module. If chi is in H prime, H star, not prime, we denote by V of chi the vector space, we've seen this before again, of elements of V in V such that H of V corresponds to a scaling of chi of H by V for all H in our vector space H. Then V is an eigenvector of H of weight chi. This comes as a proposition. Which states that if alpha is a root and V is an eigenvector of weight chi, then the action of x alpha on V is inside this element, the new element is inside V of chi plus alpha. And the proof is, well, h of chi alpha of V is equal to the bracket of h and chi alpha of V plus chi alpha h of V, which is equal to alpha of h on chi alpha of V, x alpha V plus x of x on h of x alpha of V, which gives us chi plus alpha of h acting on x alpha of V. So x alpha acting on V ends up being is of weight chi plus alpha. So x alpha adds alpha to the weight of whatever it's acting upon, essentially. Proposition. V is the direct sum of the V chi's for chi in H star. Proof: we know from basic linear algebra that non-zero eigenvectors of distinct eigenvalues are linearly independent, so the sum W as the direct sum of V chi's is a direct sum by the previous proposition. W is stable by the x alphas and we also know it is stable by h. Thus, W is stable by G. Hence, we have the direct sum of V as equal to the direct sum of W and some other G submodule V prime. Suppose that V prime is non-zero. Since we know that H is abelian and K is being assumed to be algebraically closed, so that we have all of our eigenvalues, I'm guessing, there exists in V prime a non-zero eigenvector V of H. Which V is contained in some V of chi contradicting the assumption that the fact that V prime and W, their intersection, has to be 0. They don't bother writing the brackets. Hence, V prime is 0, and V is then all of W. Alright, we have here a definition. The chi such that V chi is non-zero are called the weights of V. The dimension of V chi is called the multiplicity of chi. Example. The weights of our G, which is SLN, for the adjoint representation are the roots alpha and R with multiplicity 1 and 0 with multiplicity of n minus 1. Brings us to our next proposition. Let V be in our vector space, and the following are equivalent. V is an eigenvector for our B, which is a sum of H and the positive n. V is an eigenvector H, and also that chi alpha of V is 0 for all alpha in the positive roots. Proof, this is just from that and positive is the derived algebra of B, and that the chi alphas make a basis of our n positive. Yes, motivates definition. Well, not for motivates it, but it precedes a definition. It does motivate a definition. A non-zero V, vector V, meeting the previous proposition is called primitive. Note, all primitives have well-defined weights. And we have a proposition. Any non-zero G module V contains a primitive element. And we know that this is just Lee's theorem on the B module V, which does technically prove it. But, well, let's give them an explicit proof anyways, just to bolster our understanding of the situation here. Let S be the set of weights of V as S is finite and non-empty, it contains an element chi such that chi plus alpha I is not a weight for any indexing I. The non-zero elements of this corresponding V chi are primitive. Alright, and with that, let's move on to the next topic of irreducible G modules. Reducible G modules. It starts with a theorem. Let V be a G module with a primitive element of weight chi. Let V1 be the universal algebra of G acting on V times V be the G submodule of V generated by our V. Oh, sorry, V is our primitive element. V in V. I was confused what this was referring to at first. Then we have A, that V1 is irreducible. B, the weights of V1 are of the form chi chi minus the sum from 1 to n minus 1 of mi alpha I with mi all non-negative and c any element of v1 of weight chi is a multiple of v. The proof. Well, we have that the universal algebra of G is equal to the universal algebra of the n negative and the tensor product of that with the rest, which is RUB. Since V is an eigenvector of B, eigenvector of B, then we have that universal algebra of B on V is just K on V, hence that V1 is just universal algebra of G on V is equal, and this is just equal to U of n minus on V. I don't know why I keep trying to put an extra bracket. By Poincaré-Berghoff-Witt on the universal algebra of n minus, we see that V1 is generated by elements of the form MV, where M is a monomial in the x minus alphas, for alpha being a positive root. Thus, the M times V are eigenvalues of H of weight. Of weight chi minus the sum of positive alpha Q alpha alpha with Q alpha being positive, that gives us B. C follows from that QA's can only all be zero when our M is degree 0. So when M is essentially 1, so M times V is just V. Now for part A, suppose V1 is decomposed into the direct sum is a direct sum. So we're splitting V into V1 into V prime and V double prime. With our V equal to V prime and V double prime. Since V1 chi has to be V prime chi plus V double prime of chi. Both V prime and V double prime are weight chi. And by C, they are both multiples of V, so at least one is 0. So say V double prime is 0. Then V prime is V, and as V generates V1, we have that V prime is V1 and V double prime is 0. Alright, we have one last theorem and then a remark. This theorem, once again, comes in two parts. First off, let V be an irreducible G module. Then V has one primitive element. Only one has one primitive element. It could be unique up to multiplication by non-zero elements of K, and the weight of this element is called the highest weight of V. Secondly, we have that G modules with the irreducible G modules, I should say, irreducible G modules with the same highest weight are isomorphic. So the irreducible G module with the highest weight is, in this sense, going to be unique. The proof. If V is irreducible, it must contain a primitive element, v, and we'll say it has weight of chi. Now let v prime be another primitive element of v with weight chi prime. Since v is irreducible, our first primitive element generates v, so we get from the previous theorem chi minus chi prime is the sum of n minus 1 mi alpha I. And similarly, we have that chi prime minus chi is going the other direction. This must be sum mi prime alpha I. But we can see from these that each I and mi prime both have to be 0. So chi prime has to be chi. And C from the previous theorem applies. Now, let v1 and v2 be irreducible G modules with primitive elements v1 and v2 of weight chi for both. Then v as v1, v2 inside of v1 plus v2 is primitive of weight chi by a previous theorem the G submodule W of v1 times v2 generated by v is irreducible. Projection map pi from W to Vi is non-zero, since pi of V is just, pi I of V is just Vi. So it is, an isomorphism. With W and Vi being irreducible. Thus, V1, V2, and W are all isomorphic to one another. And we'll end this video here with a remark. this theorem produces classification of irreducible G modules to determination of the chi in H prime, which are highest weights, i.e. weights of primitive elements in some G module. And we will be making this determination in the future. But that starts our exploration here of GLN. I think we'll have one more video on this, probably a shorter one. Maybe. And then we'll go from there.